So now we're going to introduce um, Lewis structures. So how we pictorially represent ionic compounds or molecular compounds that shows us how the elements involved are either attracted to one another or are sharing electrons. And as we saw in chapter 8, periodic trends, and prior to that, in 7, valence electrons occupy the outermost or the highest principal energy level of an atom. And these are the electrons that are either lost, gained, or shared in the case of a chemical bond. Of course, ionic bonds are formed when one element, a metal, loses an electron and a nonmetal picks it up. And that, of course, is an electrostatic attraction versus an actual sharing of electrons as occurs in covalent bonds. So, you've seen these before. I'm just reminding you that you are responsible for knowing these general electron valence configurations up through 8A, which again was not, whoops, no, tried to write on that and instead I flipped to the next slide and I can't go back, so sorry. So we can write Lewis dot symbols or structures for individual elements, and all we do is write the symbol of that element, hydrogen for example, and then we use dots to indicate the valence electrons around that, that symbol. So in the case of hydrogen with one electron, we have one dot, and if you look at all the elements in group 1A, they have the same Lewis dot structure, and that's because their general valence electron configuration is NS1 for all of them. The only thing that changes is the N value as you go down that column. So they all have one electron. If you look at group 2A with two valence electrons, and remember these are also given by the group number for the metals, main group metals, they each have two electrons, and you'll notice they are placed opposite one another around the symbol. So this would be acceptable as well. Okay. We try to evenly distribute them or symmetrically distribute them before we start pairing them. And so if we jump over to 3A, you see boron with 3 electrons, one on each of 3 sides. Carbon is the first time we have 1 electron on each side. And then as we add electrons, we're also going to add dots until we complete what we're going to call an octet. Okay, so an octet is 8 electrons around an atom. And the octet rule is what drives bond formation, chemical bond formation, and ion formation. Okay, everyone wants to attain the electron configuration of a noble gas. All right, so let's look at the ionic bond, which again is the electrostatic attraction that holds those ions together in the compound. We're going to use lithium and fluorine as examples here. So we have the Lewis structure or symbol for each of these atoms as elements, neutral elements. And what happens is lithium, in order to gain that configuration of the electron configuration of a noble gas, gives up its electron to fluorine and becomes the positive ion. Fluorine is one electron away from that noble gas or a noble gas electron configuration, so it gains that electron. Okay, so the ionic bond is driven by that desire for each element to have the electron configuration of a noble gas. And this is just indicating what noble gases are present. We can write these ion transformations as a chemical equation, so to speak, where here we have the neutral atom with one valence electron, and on the product side we see the lithium ion plus an electron, a free electron, which actually doesn't remain free. That free electron, as you can see, is shown on the reactant side with the fluorine atom. So here is that electron, and it is gained by fluorine to form the fluoride ion. Okay, so this is not exactly the way we would write an ionic compound's Lewis structure. What is lacking here, and I'm going to point it out, is for any anion, we need brackets around that anion in a Lewis structure for an ionic compound with the charge outside. This symbol for the cation is just that, and it's this plus minus attraction that is holding that formula unit together. So we can use Lewis dot structures to show the formation of, for example, aluminum oxide. We have two aluminums and 3 oxygens in this compound, and we're going to run through an example of how we can use the Lewis structures to come up with that formula and actually kind of visualize how it holds itself together. Okay, so we have the Lewis symbols for aluminum and oxygen. Aluminum will lose 3 electrons, and oxygen wants 2 more electrons. So we have to have a ratio here in which aluminum can give up all of its electrons and they are picked up by oxygen atoms to form those anions. Okay, so basically we need 2 aluminums and 3 oxygens because we have 3 valence electrons to get rid of, but oxygen only needs 2. But if we have 2 aluminums and 3 oxygens, then this will even out, and we will and I want to actually show this in a different manner. So if we have aluminum 3 here, and we have oxygen here, and we have an aluminum here, and we have an oxygen here. Oh, heck. How do I want to do that? Guess I'll just do it like this. So actually we need 1 more oxygen. Okay, so this oxygen needs 2 electrons. So this aluminum is going to transfer 2 to that. This oxygen needs 2, so it can give its third one to this oxygen. This aluminum can contribute the second one here, and then of course this aluminum is going to give 2 electrons to that oxygen. So everybody has the electron configuration of a noble gas, and feels like it has a full outer shell, or it does have a full outer shell. The covalent bond is a chemical bond. And in a chemical bond, electrons are shared by 2 atoms. And this 2 is driven by that octet rule, where an element feels the need or is stabilized by having 8 valence electrons. So each of these fluorines has 7 valence electrons, and they have a single electron for each of them that aren't paired, which become paired when they form a single bond. And then they each feel like they have an octet, or 8 electrons. So this is the Lewis structure of the F2 molecule. Sorry about that. I'll try to get through this and go back and handle that. So rather than showing that bond as 2 individual dots, we represent it by a single line. So that means there are 2 electrons being shared between those 2 fluorine atoms. Okay? Other terminology, we also call these bonding electrons. And we either call these non-bonding electrons or lone pairs. Both, you might hear me say both of those terms. Either non-bonding electrons or lone pairs of electrons. And that, of course, is a single covalent bond. So let's look at the Lewis structure of water. We have a hydrogen with 1 valence electron and oxygen with 6 valence electrons. And it wants 8, or it needs 8. So that means we need another hydrogen in order to form that water molecule. This is the correct Lewis structure for that water molecule, showing the single bonds between the oxygen and hydrogens here. Now, oxygen, because it has 8 electrons, satisfies the octet rule and is in its most stable bonding state. Hydrogen, on the other hand, only has 1 valence electron. Therefore, it can only make 1 bond, and that is through sharing its electron with one of oxygen's electron, and we call this the duet rule. And because of this, hydrogens are always terminal atoms. And what I mean by that is they're always on the periphery of the structure. They will never be a central atom because they don't make more than 1 bond. Okay? So those another example of single bonds. However, we have double bonds when 2 atoms share 2 pairs of electrons. And this occurs in the molecule carbon dioxide. And this, of course, is the correct representation of that Lewis structure. And we're going to practice drawing these and go through the rules for that, for doing such. We're just introducing composition of bonds and so forth before we start. So again, oxygen feels like it has an octet, as well, both oxygens as well as carbon, with those double bonds. Triple bonds form when 3 pairs of electrons are shared, and the N2 molecule is a good example of this, where we have a triple bond between the 2 nitrogen atoms and then 1 lone pair on that nitrogen atom. And once again, this satisfies the octet rule. Each of those nitrogens feels like it has an octet, or 8 valence electrons. This slide allows us to, of course, picometers are quite small, so it's a blow up, but shows us the difference or how bond lengths are measured. And essentially, it is the distance between the nuclei of 2 adjacent atoms. Okay, so in H2, bond length is 74 picometers, whereas in HI, it is 161 picometers. And if we look at this table, we can see that as, let's look at carbon here, these 3 CC bonds. The carbon-carbon bond has a bond length of 154 picometers, but when we look at the double bond, that distance, or that bond length, has decreased. And we look at the triple bond, and it's decreased in even further. So this helps explain bond strength. As bond length decreases, bond strength increases. So it's harder to break a triple bond than a double, than a single. Okay. Oh, sorry, I forgot that was there. So we are comparing ionic versus a covalent compound here, and this also is an indicator of, or explains, I should say, the difference between the strengths of an ionic bond and a covalent bond. So remember that ionic bond is an electrostatic attraction. The covalent bond is a sharing of electrons. And when we compare sodium chloride to carbon tetrachloride, of course, sodium chloride is a solid, carbon tetrachloride is a liquid, but look at the melting points. Melting point of sodium chloride, 801 degrees Celsius. For carbon tetrachloride, minus 23 degrees Celsius. So that is an indicator of the strength of that ionic interaction compared to the interaction between covalent molecules, which is quite low in comparison. We haven't talked about molar heats of fusion or vaporization yet. That comes with chapter 11, but you can see that sodium chloride is much greater than carbon tetrachloride Boiling point for sodium chloride, 1400 degrees compared to 76.5 for that covalent compound. Also look at solubility. Sodium chloride is very soluble in water, and carbon tetrachloride is not, and we will specifically address why that is after we talk about the polarity of molecules. So with respect to the properties of ionic compounds versus covalent compounds, it's highly dependent upon the strength of that electrostatic interaction. So the ionic bond is much stronger than a covalent bond. Now, within a covalent bond, we are sharing electrons. However, those electrons aren't necessarily shared equally. It depends upon the electronegativity difference between each of the elements that are bonded together. So a polar covalent bond or a polar bond is a covalent bond that has one atom or element that is more electronegative than the other, and the shared electrons spend more time around that more electronegative element than the other. And in this case, the example is hydrofluoric acid. Fluorine is, we know, the most electronegative element on the periodic table. Hydrogen is less electronegative, so the electron density is going to be shifted toward that fluorine atom. And we draw this arrow with a cross here to indicate a dipole. So this is describing a dipole in which the more negative end is at the end of the arrow and the partially positive end is at this end of the arrow. So in a polar covalent molecule, we need, first of all, we must have a polar bond and some kind of asymmetry with respect to the dipole. And this one satisfies both of those. And we'll talk more about that in chapter 10. Partially negative, partially positive. All right, so we've discussed this in the previous chapter. Electronegativity, the ability of an atom to attract electrons toward itself in a chemical bond. The other trend that was mentioned when electronegativity was discussed, but I crossed out because they are actually slightly different, is electron affinity. This is a measurable property. And we aren't going to get into that, but it has to do with the amount of energy that's required to accept an electron, essentially, from another element. And electronegativity, as I mentioned in the previous material, is relative. These values were assigned by Linus Pauling, and they are relative to the fluorine atom. And we did discuss this electronegativity trend in chapter 8, but here's a reminder that when we move from left to right across the periodic table, electronegativity increases, and when we move from top to bottom in a family, electronegativity decreases. So we can classify bonds by the difference in electronegativities between the atoms that are bonding together. So if there's zero difference, we have, and I'm going to add something here, a pure covalent bond, or pure nonpolar covalent bond. If we have a difference in electronegativity that's greater than or equal to 2, we have an ionic bond. And I'm going to adjust this. I'm going to say that this is zero difference is pure nonpolar covalent. We can also have, I'm going to say between 0.5 and less than 2 is polar covalent. And 0.1 to 0.4 is just nonpolar. Pure nonpolar covalent would be zero difference in electronegativity. Oops, sorry. So there's not a real transfer here, so I don't like those words, but the electron density is greater around one of the atoms. And that atom would be the more electronegative atom. And when we have an ionic bond, of course, we've got a total transfer from one element to the other. And let's see how we're doing here. Got a couple more slides. So let's classify these bonds as ionic, polar covalent, or covalent. In order to do that, we want to determine the difference in electronegativity. And I think this might be described in the next slide, but I am going to do it here, and then you can read if you want to review this again, you can go through and read the next two slides, or the next one at least. I'm not going to read that to you, but it's there for your reference. So the bond in HCl. So we want to look up the electronegativity values for hydrogen and chlorine. Chlorine is its electronegativity value is 3.0, and hydrogen's is 2.1. So we'll subtract the smaller electronegativity, of course, to get the difference in electronegativity, and we get 0.9, which is greater than 0.5, less than 2, so this is polar covalent. The bond in KF, fluorine is the most electronegative element at 4, potassium's electronegativity is 0.8, so the difference here is 3.2, which of course is greater than 2, so this is an ionic bond. And the CC bond in this compound, so carbon's electronegativity value is 2.5, and if we subtract those from one another, we get 0. So this is pure nonpolar covalent. And if we had a difference between 0.1 and 0.4, it would just be nonpolar covalent. And as I said, here's the rationale and the solution for that. And you can read through that if you wish. I'm not going to read it to you. We just